Okay, and we're recording. So this book chapter 5. Oh, whoops. I don't want yellow. Let's get the black here. Already off to a bad start. Okay, so this chapter in the book, chapter 5, is all about work and energy. And work and energy. Okay, and we'll start with the idea of work. So what is work? Work is done when a force moves an object. Okay. So the way we write that down in physics is it's a force times displacement. And we'll refine this as we go through, but this is just the quick introduction to work here. And so for work, we use the symbol W. For force, we've been using the symbol F, right? And for displacement, we use delta X, although sometimes we'll see it written as F times D, where D is some distance that the object has traveled in one direction. Now, of course, force is a vector, right? And so is displacement. And so we can actually improve upon this definition here of work by writing it down in terms of vectors. But let's first understand a quick little example here. Suppose that we have a block here, and it has a mass m, and this block is on a level table here. See if I can straighten that out a little bit. There we go. I see a chat. Isn't this chapter 6? Oh, is this chapter? This is chapter 6, isn't it? Yeah, my bad. Chapter 6. Let's go up and fix that real quick. Chapter 6. Okay. So if we apply a force to this block here, then of course this block will accelerate, right? F equals ma. So we can even note that here. So recall from the chapter on Newton's laws that we have a force applied to a mass, then it's going to accelerate. And so some later time, this block will be over here, and I'll use dotted lines here to indicate where the mass will be the future time. Okay. And it's traveled a distance d, or it has been displaced by an amount delta x. Okay. You can use x or d if you want. Okay, well, this applied force pushes this mass, this displacement delta x. Okay. And so the amount of work done in moving this mass is equal to the force applied times that displacement delta x. Suppose now that instead we have a similar scenario here, and I'm actually going to cheat here and copy paste. Suppose now we have a similar scenario, but let's modify slightly. If I change the direction that the force is applied, we can ask the same question. Suppose I apply the force in this downward direction, okay, and the mass moves to the right a distance delta x, but now it's pretty clear that the force F is not the force that's moving the mass, right? Compare with the situation above. Above, it's pretty clear we're pushing this mass to the right. And so that force is the one that does work to move that box. Well, here in this situation at the bottom, if we apply a force on this block from above, right, that's not going to be a force that's going to move this mass, a displacement delta x. And so this force here, we would say does 0 work to move this block, okay, because that force doesn't actually move the block. So let's go ahead and make a little note here for ourselves on the side. Go ahead and type a note. So this force doesn't move the block, okay? And so the point is, okay, Leanne. So if there's no horizontal movement, the work is 0. No, so what we're saying is that the force is being applied from above, but the block is still displaced by an amount delta x. So an example of how that might happen is the block could be moving with constant velocity, and we apply a force from above. So the force from above would have no effect on the block's velocity in the x direction. So it would still be displaced by an amount delta x after some time. And so in that situation, this force doesn't do any work to move the block, but the block could still be displaced by an amount delta x. So what we're going to say now is that only forces which are parallel to the displacement do work. Okay, so an important point here. So only forces parallel to the displacement do work. Okay. So does that answer your question? Okay. Okay, good. So yeah, only forces which are parallel, and I probably should highlight this maybe together here. Forces that are parallel to the displacement. Okay, those are the only ones that do work. So we can improve our statement before about force times displacement by now writing it in the following form. We can say that the work is equal to the force that is in the parallel direction. So remember these two bars from your geometry class way back in like 9th grade or whatever. This means parallel, right? So you'll see that notation in the book here and there. I think we've probably already encountered it a couple times. I might have even used it before. Times the displacement delta x. So now it's just the parallel component of the force that does work. And we understand that because if we were to apply a force from above on that block, well, that force isn't really doing anything. It's just kind of there. And there's going to be a normal force due to the ground, right? That kind of balances that out. And so nothing's really going on interesting there. So the parallel component does work. Well, I mentioned before that force and displacement are vectors, right? So what we can do now is we can take a look at what happens if we apply a force at an angle. Okay, so let's go ahead and draw again another mass. Here's our mass. Let's get a horizontal plane here, mass M. And now we'll apply a force at an angle here. So I'll come in like this. Okay. And of course, we can always break a vector down into its components, right? And so if this is the angle theta here, then we have our x component of the force is the magnitude of the force times cosine theta. And the y component is magnitude of the force times sine theta. Okay, so while you're copying that down, let me go ahead and kind of get the dotted line box in here. So this box, again, it displaces an amount delta x, just like before. But now the component of the force which is parallel to the displacement is this one here. It's the one I'm going to box in red, the x component. So we'll go ahead and we'll say over here on the side. So this is the parallel component of the force. And so now if we want to, again, change how we write down the formula for work to account for the fact that we could have a force coming in at an angle, we could say, instead of the parallel component of the force, we could say F times cosine of theta times delta x. Right? Okay, and so now we've got just a couple cases now. So if we apply a force in the direction that the box is going to be displaced in, then we just have F times delta x. But if we apply a force at an angle theta, well, then we can use this formula here, F cosine theta, to get the parallel component and then multiply by that displacement delta x. Okay, and this formula is actually nice because it tells us that if theta is 90 degrees, in other words, we apply a force from above like so, right? But the displacement is in this direction. So we have a force like this. We have displacement in this direction. Then the work is 0 here for this case, because the cosine of 90 degrees is 0. Any questions about that? The session is being recorded, yes. I'll get that post on YouTube as soon as we're done here. I'll start posting that, and it'll be up in a couple hours. Usually if you want to watch the version of the recording that's like 360p or whatever, that one's usually up pretty quick, but it's the HD processing that takes like a couple hours. So if you want to wait for the high quality video, that usually takes like 3 hours or so. Okay, so let's do an example now, right? So we've got this concept of work under our belts now, so let's try and apply it. So for those of you maybe are still copying down, I'll leave a little bit of space there. So I will go ahead and grab an example. I wanted to do this one here. Okay, and so we will have a picture to go with this example. So I'll draw the picture first. So we have a crate with a mass M, and this crate is being pulled on with a force. It's labeled FP, so the pulling force, at an angle of 37 degrees. The mass of the crate is 50 kilograms. And the displacement of the crate when it ends up at its final destination will be 40 meters. And the magnitude of this pulling force, the magnitude, so let me write it without a vector symbol, will be 100 newtons. In addition to the force that is pulling on this box, we're also interested in a friction force acting on the box, which is only 50 newtons. So we have a friction force, and the magnitude of that friction force is 50 newtons. Okay. Now, what's the question? So the question is, what is the work done by each force on the box or the crate? Okay, and that is part A. Part B is, what is the net work done on the box? What is the net work? Okay, so we can calculate an amount of work that each of the forces acting on the crate does. Don't forget about the gravitational force, right? The weight. Don't forget about the normal force between, due to the contact of the crate with the ground, right? And we have the friction force, and we have the pulling force, right? So calculate the work done by each force on the crate, and then what is the net work done on the crate? So before I let you guys work on that, why don't I ask the question, so what does it mean by the net work? So whenever you see that word net, what does that mean? Like, for example, what is net force, for example? So somebody tell us what the word net means.
Sum of?
The sum, exactly. So it means the sum. So when we calculate the amount of work done by each of those forces, we would then add them all up, and that would give us the net work. Okay. And I think you guys can already intuitively see some of the forces in this problem will do zero work, right? And some of the forces will do non-zero work. I'll leave you with one more bit of information before you guys kind of work on this. And that is that it is possible to do negative work. Okay, it is possible to do negative work. When is that the case? It's the case when a force is in the opposite direction of the displacement. Okay, when the force is opposite the displacement, the work done by that force is negative. Okay, so I'll give you guys a couple minutes to work on that. Once you've calculated the work done by a certain force, go ahead and type that answer that you got into the chat so that way everyone can kind of compare their answers. And there's that check that you guys can go through. So just throw your answers into the chat as you get them. And then, maybe somebody will make a mistake and they can correct their answer and so forth. Has anyone got an answer for the work done by the force due to gravity or the weight of the crate? Okay, good. So we have a couple people giving some input here. Good. Do we have the work done by the normal force? Okay. Anybody have the work done by the friction force? Evan coming in with answers here. A lot of answers. Liliana has the same answers. Same. Okay. Anybody need more time? I know a lot of you sometimes don't want to write in the chat, so let me know. Remember, with the friction force, you can use that formula with the cosine theta. but you have to think about what is theta in that case. Okay. Yeah, so it definitely should be negative because it's opposite the direction of motion. And some of you have already given given your answers for FP, the pulling force. So I'll just go ahead and ask it. So what is the work done by FP, the pulling force? Okay, does anybody need any additional time? Let me know if you need additional time. Okay, no one is speaking up, so we'll go ahead and we'll move forward then. I will, for the most part, not cover the entire example because I feel like, if there's no questions, then everybody's kind of getting it, right? So let me just go ahead and show the one calculation here for the pulling force. So the work for the pulling force, I would write down F cosine theta times delta X. And then the force that I'm using there is the 100 newtons pulling force. And then it's cosine of that 37 degrees, right? Cosine of the 37 degrees. And then times the delta X of 40 meters. And then when you crunch the numbers on that, I believe those of you who put your answers there have it correct. 3,100 or 3,200, I guess, if you want to have the right sig figs or something. So whatever you got there, can maybe round it to 3,200, which is the answer that they give in the book. But maybe it's a little bit ambiguous because you have like zeros on the ends of all these numbers, right? So it's a little bit ambiguous. So I don't blame you guys. So that's the, excuse me, it's not newtons. Notice it's newtons times meter, right? So let me not make a mistake here. So newtons times meter. And we use a new unit for this newtons times meters. We call them joules. We use a capital J for that. So 3,200 joules. And this is a positive amount of work. The angle here is 37 degrees. For the friction force, you could think of theta as being 180 degrees, in which case the cosine would be -1. And so you would get negative work. Okay. Now, I didn't ask in chat, so let me go ahead and ask. What is the net work then? So add up all of the amounts of work that you calculated. So net work equal to. So add up the two answers that you got. So what is the answer for the network? Okay, we have one answer here, 2,995 joules. Interesting. I think some of you are off by an order of magnitude on your friction calculation. So yes, I agree with 1,200. These two answers, which are close to 3,000, I think you are off by a factor of 10 on your friction force. So double check that. Or sorry, on the work done by your friction force. If you are getting the answer 1,200 joules, you are correct. Yeah. So the friction one, I noticed in the chat also, Kevin, you have to check yours too, I think. Yeah, you had minus 200 in the chat. I'm not sure if you had that written down. Yeah. Okay, so good. So it's minus, what was it again? 1,200, minus 2,000 for friction. And it was a positive 3,200 for the work done by the pulling force. And so our net is 1,200 joules here. Okay, so good job. All the perpendicular forces do 0 work. So that is how you calculate the work done by a constant force, okay? So this is, so work done by a constant force. Constant force. Okay. So work done by a constant force. Work is F cosine theta times delta x. How do we calculate sorry for the handwriting here, work done by a variable force? Does anybody remember all the way back to, I believe it was in chapter 2, we did a lot of problems with constant acceleration, right? But we did look at some problems where the where the acceleration was not constant, but we did so using graphs, right? So we used graphs of the acceleration. And so we could have like these trapezoid type shapes, right? Different kind of shapes for the acceleration. And what did we do in that case to find the velocity when we had this variable acceleration? So question for you guys. So what did we do to find the velocity when we had a graph for the acceleration and it wasn't constant? So how did we go from acceleration to velocity? So Kevin says, I think we got the area under the curve. Good, that's exactly what we did. And that's exactly what we're going to do when we have a variable force. How do we understand that? Well, when we have a constant force, so if we have a constant force over here, And that's often what we do. For those of you who are taking the calculus version of the class, let me just give you guys a little bit of insider info. Watch the pre-lecture videos, by the way. Everyone should watch the pre-lecture videos that I post on Mastering, those Anderson videos. Some of them contain calculus. So if you're in the 205 class, once he writes down some calculus, you have a choice. You can continue watching. Maybe you've taken calculus, so you kind of understand what's going on. Or you can stop watching at that point, or maybe skip through that part and just kind of see what the answer comes out to. Oftentimes the calculus reduces down to something very simple, like just multiplying, but not always. But for those of you who are in the 210 class, definitely watch those videos for the calculus parts, just to really enhance your understanding. What we would do here for work in terms of calculus is we would look at, for a variable force, we would say, instead of doing a large amount of work, we would do a small amount of work, dW. And that would be equal to the integral of the force over a small displacement dx. Okay, so just a little bit there for you guys who are in the 210 class. Okay, so dw is the integral of f dx. I'll give you guys a second to write that down. And so, as I was saying, or as Kevin pointed out, to go from acceleration versus time, to velocity versus time, we need the area under the curve. So area under the curve. So we need to plot acceleration, or sorry, we need to plot force versus displacement. In other words, force versus x. So F versus x. So constant force, F versus x. And we can see on the F axis here, on the Y axis is our X axis. Excuse me, the vertical axis is our force axis. The horizontal axis is our position or our displacement axis. If we have a constant force, let me try and draw a real straight line here. This is a constant force, right? So it has only one value. Well, we can imagine that if our box started here at its initial position, call it xi, and then the box moved to its final position, x final here, well, then the displacement there would then be delta x, right? And this region up top here, this is our constant force being applied. I kind of wrote that maybe confusingly. So notice that the force is constant here at the top. That's our force, let's call it F. That is the height of this rectangle. So F is the height there of the rectangle. So if we calculate F times delta x, this is the work done on that crate or that box, okay? So how about if the force is not constant? What do we do? Well, we do the same thing. We calculate it as the area under the curve, except now it's not a simple rectangle anymore. So suppose, let's not get too complicated. Suppose we have a force which depends on x. Okay, so, and actually, let's not make it go straight through zero. Suppose we have a force like this, okay? So it's linear just to keep things simple still, but not too simple. And now, again, as before, we have some crate, some mass, which has an initial position, and it ends up over here at its final position. And there's a delta x associated with that, final minus initial. but the force is changing. The force is getting bigger as we push this thing. We're pushing with more and more force as we push on this box. Okay, so again, the width here is delta x, but the height is not always the same f, right? Well, we can kind of break this thing down into two segments where the height here is, say, F initial, where this is the force that we kind of started with. So F initial here, right? And then where do we end up at over here if we need this height, which of course we need this height right here is going to be, if this is F final, this height here is F final minus F initial, right? So you just have to go about calculating that area using triangles and rectangles, right? And, you know, we won't do anything too complicated in this class, right? We're not going to have some crazy function, you know, to calculate the work done on some box. So this is the F axis, the force axis, and this is the position axis. So don't expect any questions where the force is anything more than linear, okay? Maximum variable force we'll have is something that's linear. So this is a variable force. And in this case, we've shown a linear force. Okay, so any questions about that? That's maybe a good place to stop and ask, let you guys ask questions if there are any. So is everybody with me there? Give me a message in the chat if you guys are with me on that. So you should think kind of in terms of that acceleration versus time. How do we get to velocity? Well, we get to velocity by getting the area under the curve. So if we want to know the work done by a force, we can plot that force versus displacement and then calculate the area under the curve. I'll go ahead and write that down for you guys as well. So this is what we do here. So let's go ahead. Let's get a little bit colorful here. So here's the point of things here is when we have a variable force, or any force for that matter, the work is the area under the plot of F versus X. And maybe, so area is what we want. When we're after work, we want to look at area under F versus X. Okay. So in the book, they don't really give an example of work done by a varying force, but there is going to be one example which is of particular importance, and that is known as Hooke's law. So let me just briefly mention Hooke's law, and it may actually come up later in the chapter. So let me briefly mention Hooke's law. So this is a little side topic here. Whoops, side topic, Hooke's law. This is an example of a nice, simple linear force. So what Hooke's law says is that suppose you have a wall here. So this is a wall, and you attach a spring to the wall. And you put a mass at the end of that spring. Here's our floor here, or tabletop. And the spring has a natural resting length. Okay, so the natural resting length of the spring basically means the spring is not stretched and it's not compressed. Okay, so not stretched or compressed. Then that spring will have a natural resting length. We call it like L or something. Okay. The rest length of the spring. But if you stretch the spring, I'm going to go ahead and cheat a little bit here. I'm going to copy paste this. But if you stretch the spring, and I'm going to just do something crazy like this here, so just taking advantage of paint. So now it's stretched. Okay, so this was the old length, something like that. And then this is an amount of stretching, delta x. Okay. And we all know what happens when we stretch a spring, right? If you have like a slinky or something, right? That's kind of like a spring. You can stretch it. And if you stretch it out and you let go of it, then it comes back, right? It comes back to where it wants to be, which is in equilibrium. No net force. Since you've stretched it, you've applied a force to it to stretch it. And now it applies a force to return itself towards equilibrium. So let's maybe use another color here. So when the spring is stretched to the right, there's a force that restores the spring back to its equilibrium position. In other words, its resting length. Okay. And that force in magnitude is minus K times delta X. And the minus sign here means the force is a restoring force. That just means that the force wants to bring it back to its natural state. So it wants to return to its rest length. Okay. And what is this K thing here? This K here is what we call a spring constant. So the K here, this is what we call the spring constant. So every spring is different. You can have a really sturdy spring, which has a large spring constant. It's really hard to stretch it. And it will have a really big restoring force because of that. You can have like a slinky, which has a very small spring constant, and it's very easy to stretch. Right? Of course, delta X is the same as it's always been. That's our displacement, right? Delta X, we usually reserve that for displacement. And in particular, this is displacement from equilibrium or displacement from the rest length. Okay. So what would this thing look like if we were to plot it? And how might we calculate an amount of work done in stretching a particular mass connected to a spring? Well, it's a force which varies as minus x. So it's a downward sloping plot. Okay, so let's scroll down a little bit here. Don't want to scroll too far down in case you guys are still writing. So let's try to plot that now. So let's plot Hooke's law, a Hooke's law force. Just a little history while I'm writing here. Hooke and Newton were not very good friends. Hooke used to try to take credit for a lot of stuff that other people did and kind of like claim them as like his own ideas. There's like a whole history of things that Newton published that Hooke tries to take credit for, even though he never wrote any, he never published any papers or books or anything on those topics. Oh, and I've kind of, since I was chatting with you guys, I kind of messed up there. Since this is downward sloping, I probably want to draw something like this. So yeah, that's interesting. You can maybe read about that on the Wikipedia page. I think it's on, if you just look up Isaac Newton on Wikipedia, or even just Hooke. I forget his first name, but look up Hooke's law and then you can find him. Yeah, so it's kind of interesting. Hooke was kind of disliked by a lot of people because of that. So we have here on the vertical axis the force for Hooke's law. And on the horizontal axis, again, we have the displacement. And Hooke's law would literally be a downward sloping line which crosses through the 0 point there, the origin. And what would the slope of this line be? Can somebody tell me what the slope of this line would be? Go ahead and write that in the chat as well. So what is the slope of this line? Right, minus k, right? So we have the force on the vertical axis, and we're plotting that versus the displacement, delta x. So the slope would be that minus k there. So we'll go ahead and put that in there. And that k, again, is called a spring constant. Maybe I'll put the minus sign as well. There we go. And so if we wanted to, as a matter of fact, let me put that on the other side, and then we can talk about the area there as well. So the slope is minus k. So if we wanted to calculate now the area, well, we know that the Hooke's law force is equal to minus k times delta x. And of course, if we were to displace the spring from, let's say, 0, and actually I'll change colors again here. If we were to displace the spring from its rest length out a distance delta x, what would be the area of this triangle here? So what would be the area of this triangle? Does anybody, are we clear on what's being asked here? So what's the area of that triangle? So we know the base and we know the height. Oh, yeah. So it's going to be the work, right? It's going to be the work done to stretch the spring. But what is the actual value? Right. So exactly. So Christine, so does everybody see that how we calculate the area there? We just want to use a simple 1/2 base times height, right? So the area, which is going to be the work, that's going to be 1/2 times the base delta x times the height, which is minus k times delta x. And if we combine all those terms, right, we get minus 1/2 k times delta x squared. And usually for springs, once we kind of introduce them, we don't always like to write delta x squared. Sometimes you'll see it written down in the following way. So it'll be minus 1/2 k x squared, where we already understand that x is the amount of stretching or compressing in the spring. Okay. And we've gotten an answer now for a variable force for Hooke's law. Okay, so are there any questions about that? Was everybody able to understand why it's 1/2 kx squared with this minus sign here? So we just want the area here of this triangle. Okay, so no questions. So we'll go on to the next section, which is kinetic energy and the work energy principle. Give me 1 second here.
Sorry, Professor,
Go ahead.
can you give us an example where you would see like a variable force, or is it only in spring?
So if we want to talk variable forces, we've already seen one, and that is the gravitational force. So things get complicated when we try to calculate work done by variable forces, especially for this course where we only have trig. We really need to break out calculus if we want to do anything more. It's kind of easy to calculate areas for triangles and rectangles, right? But it's maybe pretty difficult to calculate the area, for example, under something like this, where it's 1/r² dependence. And then maybe we have a radial displacement. So it'd be like a delta r instead of a delta x. But you can still follow, if you're in the 210 class, those of you who are in the 210 class, you can still do something like this, which is the integral of that force due to gravity. And instead of integrating over dx, you can integrate over dr to get the work, because it's a radial displacement instead of an x displacement. And so I'll leave it at that. I won't say much more than that, because things get complicated once you have variable forces. This is probably the best example of a variable force that we could do with our tools. So it's the area under the curve. And if you actually open up the textbook and read that section, it's just a very short kind of like 1 or 2 paragraphs on variable force. So it's something that we're trying to avoid as much as possible. Okay. You may get a question about it on the homework, something like that, but just always go after the area under the curve. Okay. Any other questions about that? Okay, so we'll go ahead and move to, I'm going to go ahead and actually clear this, and we'll move to kinetic energy and the work energy theorem. So kinetic energy. We'll start by first looking at what we had for the work previously. We said that work was a force parallel to a displacement. So F parallel times a delta X. Let's go ahead and take a look at a specific case again, where we have a crate on a level table here, or the floor, something that's, no angles involved here. And suppose that we apply a force, a constant force, to keep things simple here, F. So we can drop the parallel part. We don't need to consider the parallel component because it is parallel. And let's assume here that we have a displacement, right, of delta X. I'll go ahead and draw in the dotted lines here again. So that's our mass M. So it's a force being applied to an object, and it has a displacement. So there's work done by that force. And I mentioned kind of in passing before that we could apply, Newton's second law, and we could write this force as F equals ma, right? So let's go ahead and do that real quick. So the force, replace it with ma times delta X. And then sometimes you may even see delta X replaced by D. So we'll replace delta X with D. And so there's a mnemonic that people like to say to help them remember some of these formulas that we come across here. And this is the mnemonic right here. So they say work is mad. And that can help you remember this formula. And the reason I bring this up, not only is this useful, but it's nice to transition from this formula into this idea of kinetic energy. And so you guys may remember a formula that we had in chapter 2 that was kind of different from the other formulas. It had velocity squared in it, right? So it was the only formula that we had where we had velocity squared. And the formula looks something like this. 2 times the acceleration times the displacement in the x direction plus the initial velocity squared was equal to the final velocity squared. You guys remember this formula from chapter 2? So let me know if you remember this. If you don't remember this, can let me know and I can tell you maybe where to find this section in chapter 2. Okay, so it looks like, okay, so a good number of you do remember this, so that's good. Okay, so you see it is possible to remember formulas, right? Okay, so so what do we do here with this? Well, notice that the left side looks an awful lot like the expression for the work, right? So maybe we'll use pink here. So this piece right here looks an awful lot like this piece. So let's go ahead and isolate that piece. Okay, so we'll isolate it, bring it over here. So we have A times delta X, right? And then we'll go back to black here. So is equal to 1/2, and I have to subtract V initial squared. So we have a V final squared here minus a V initial squared. Okay. But there's one little bit that's missing from this, and that is the mass, right? We don't have the mass on the left side of this equation. So let's go ahead and multiply it in. So let's multiply by the mass on both sides. So multiply both sides by the mass. And then the left side becomes the work done on some object by a force. And on the right side, we have this new quantity we have not seen before, and that is 1/2 mv final squared minus 1/2 mv initial squared. Right? Now, what do we call this thing on the left side? Well, first, before we give this thing, oh, sorry, I think I said left side. What do we call this thing on the right side? Before we give this thing on the right side a name, let's define a new quantity, this 1/2 mv squared thing. So define 1/2 mv squared is equal to this thing that we call kinetic energy. Okay. And now what is kinetic energy? Well, kinetic energy is energy that something has due to its motion. Notice that the thing on the right side, if we actually look at this expression here, I'll put a green box around it. If we look at this expression here with a green box, on the left side, we have something to do with displacement and a force. On the right side, we have something to do with velocity, right? Whenever we have energy associated with velocity, that's going to be kinetic energy. So any energy that we refer to that has to do with the motion of something, we call that kinetic energy. Later in the chapter, as a matter of fact, in the next section, we'll talk about energy due to something's position. We call that potential energy. Okay, so this is kinetic energy. So we'll go ahead and finish that thought off. So kinetic energy. So kinetic energy, we use Ke, kinetic energy. And this is energy due to motion. Remember, motion is kind of synonymous with velocity, right? So it's energy due to motion. Okay, so now that we've defined this quantity 1/2 mv squared as the kinetic energy, then we're ready to talk about the right side of this expression here. Maybe we'll put this in purple. And so we say that whenever we do work on an object, we always change its kinetic energy. Okay. And as a matter of fact, we should be very precise here, and we should say net work. The net work done on an object or some body is equal to the change in its kinetic energy. So for example, suppose you're trying to push a crate across the floor, right? So I'm moving a bunch of boxes around over here, right? So I have to push some boxes around on the floor. And sometimes I'll push on a box with a certain force, and that box will move with constant velocity. What that means is that I've only applied a force equal to the friction force. So if the force of friction is equal to the force that I apply, then the velocity will not change for that box, right? So the net force would be 0, so there's no acceleration. Likewise, if the net force is 0, then the net amount of work must also be 0. And so there would be no change in the box's kinetic energy. Okay, so if the net work equals 0, no change in kinetic energy. Right. Now, we went through this process of deriving this expression and kind of defining this new quantity in a very kind of simple way, where we assumed we had a constant force and the displacement was in the direction of that force. And so there was no cosine theta or anything that was showing up in our expression. However, if we use calculus, we can show that this expression here is true in general and is actually a mathematical statement. It's called the work energy theorem. Whenever you see the word theorem, that means that, it's always true, right? Work energy theorem. And I can briefly show how to get this work energy theorem using calculus. It requires knowledge of the power rule for integrals and knowledge of the chain rule for derivatives. So I'll show that just real briefly here. So those of you who are in the 205 class, you don't really need to pay attention to this, but just to add to the understanding here for the 210 class, because I really haven't been giving them much extra. So I kind of want to do that here. We start by writing down the fact that the acceleration is the change in velocity over the change in time. And we apply the chain rule to this derivative. So we write dv over something times something over dt. And whatever we write on the top of dt, we have to write on the bottom of dv. And the only thing that we have really to write there that we haven't written down yet, right? In physics, we have x, we have v, and we have a. And so the natural thing to write down here would be dx. So we'd write down dx on both sides. And when we do that, we see that we have the velocity here. This is the velocity. That's delta x over delta t. Those of you who are in the 205 class, these d's, you can think of them as deltas, and everything that we've done so far still works. So that's the velocity. And then this thing dv divided by dx, leave that as is. The next thing to do, okay, we have this is our right-hand side, and this is our left-hand side. If I take the two sides and multiply by the mass, on the left side, I have a force. You actually keep the colors here. On the left side, I have a force. And on the right side, I have some object. I don't really understand what it is yet. But what we're going to do is we're going to take this dx and move it to the other side. Okay, so we're going to move this to the other side. So what does it look like? It looks like the force times dx is equal to mv dv. And the left side I had already mentioned for you guys. This right here is a small bit of work, a force acting on an object. And there's a small displacement, dx, and so that would be a small bit of work. And so the natural thing to do here would then be to integrate both sides, like so. And we would do so from some initial velocity to some final velocity. And over here, we would integrate from some initial x position to some final x position. Regardless of whatever this integral is equal to, we could calculate for a constant force if we assume F is constant. That doesn't matter. Whatever F is, if F is a variable force or if it's constant, the left-hand side is equal to the net work by definition. On the right-hand side, we have an integral which looks an awful lot like the integral of x dx. So x has a power of 1 up here. We can apply the power rule, which gives for our answer 1/2 x squared plus some integration constant. Of course, in this case, we have the limits v initial and v final. And so we won't have this integration constant c here. So for our final answer for this integral, we'll have 1/2 m v squared evaluated at the initial velocity and the final velocity. And remember, we have to subtract those two. So we end up with 1/2 m v final squared minus v initial squared, which gives us the expression that we're looking for, 1/2 v final squared minus 1/2 m v initial squared. Which by definition, again, if we define the kinetic energy as 1/2 mv squared, then this is the change in kinetic energy. And so I've proven now that it does not require the fact, or rather it's not necessarily a fact, that F has to be constant. So in general, this is a mathematical statement that the network is always equal to the change in kinetic energy. So that's the proof of the work energy theorem using some calculus. So those of you who are in the 205 class now, hopefully you're paying attention again, or hopefully maybe you learned something from that. So let me just go ahead and say, Phys 205 students, are you with us? Okay, so here's what we'll do. I'll give you guys an example, and I want to take a break because I've been going for like an hour and some number of minutes. So I'm sure you guys want to have a little bit of a short break as well. So what I was thinking is I'll give you guys an example, and then maybe we'll do like, once I write that example up, I'll just say, okay, 15 minutes. If you finish the example in 5 minutes, then you'll have a 10-minute break. If you finish it in like 7 minutes, then you'll have like an 8-minute break. Okay, but if you finish like early, you finish it in 2 minutes and you get a little bit extra time as a break. Okay, so I'll write down an example now, and then I'll give maybe like 15 minutes. And so that'll be our break time. Okay. All right, so example. So how much net work is needed to increase well, let's use the language to accelerate a 1,000 kilogram car from an initial velocity of 20 meters per second to a final velocity of 30 meters per second. Okay. We're going to assume a constant acceleration. Which means we get to assume a constant force as well, right? So assume a constant acceleration, assume a constant force. Looks like an S. Acceleration. Okay, so that's the question. It shouldn't be too difficult. If it seems kind of difficult, then probably you might be overthinking it. So use the equations that we've just developed there to tackle this question. It is 7:22. Let's assume 7:23 is going to come soon. So we will meet back at 7:38. Okay, so 15 minutes. Go ahead and finish off that example. And if you finish a little bit early, then you get a little bit of a longer break. Okay, so I'll see you guys in 15 minutes. Don't forget to type your answers in the chat so others can check theirs as well. So when I come back, I can take a look at the chat and make sure everybody is getting the correct answer. All right, so I'll see you guys in 15. Can you guys hear me? So I've taken a look at your guys' answers there. And this is one of those situations where you have a bunch of zeros in your answer. You probably should write it in scientific notation. So I'd invite you guys to do that in your notes. So I'll run through this real quick just to show you how I would do it here. So how much network is needed to calculate, to accelerate a 1,000-kilogram car from 20 meters per second up to 30 meters per second, assume constant acceleration. Well, as a matter of fact, this bit right here doesn't even actually matter, the fact that it's constant acceleration. I just kind of threw that in because for the 205 class, we kind of did everything with constant acceleration. So hopefully that wasn't too confusing. Hopefully not confusing at all. But what we need is the fact that the network is equal to the change in kinetic energy, which is equal to 1/2 mv final squared minus 1/2 mv initial squared. And so that would be 1/2 times 1,000 kilograms. And then I'll put some big brackets here. The final velocity is 30 meters per second squared, square that, and then subtract from that the 20 meters per second, the initial velocity squared. And probably you guys could do this one in your head probably. So this is like 500 kilograms here for the units. Let's just take the units all the way out. Now we know it's going to be joules. So kilogram times meter squared per second squared is a joule. And this is 900 for the 30 squared minus 400 for the 20 squared. So it's basically 500 times 500. So 5 times 5 with 4 zeros. So I'd probably write this as like 25 times 10 to the 4th joules. If you did 2.5 times 10 to the 5th, that's fine. If you did 250 kilojoules, maybe that's a nice way of writing it as well. So 250 kilojoules. And before we get started on the next topic, actually, I want to pose the following question to you guys. How much energy is this? We have no idea how much energy that is. And so I now pose to you the following conversion factor. 1 dietary calorie is equal to roughly 4,200 joules. So I'll make that an approximately 4,200 joules there. And so now I'd like you guys to calculate this answer in terms of calories. So convert, unit conversion problem. So convert your answer to dietary calories. Okay, so that's your task. So convert that answer that you got and for those of you who want a more precise conversion factor, I just had to look it up real quick. 4,184 joules to be exact. That is the standard value. As a matter of fact, some people actually, this is always confusing to me too. Some people actually use the following value with a 6 instead of a 4. I always find that interesting that it's always either a 4 or a 6 in the last digit, but it's never anything else. It's kind of strange. You can always just round it off to 4,200. That's kind of what I remember mostly. 4,200 joules per dietary calorie. Go ahead and punch your answer into the chat once you get that to compare with everyone else. About 60 dietary calories. So now we have grounds for comparison, right? So this would have you believe that this 250 kilojoules, or 250,000 joules, is not that much energy. And it really isn't that much energy. The problem is like most things, when you try to convert energy from one form to another form, for example, like if you eat some food, the food has a lot of chemical energy stored up in the bonds of the molecules, and your body breaks those bonds down and forms new bonds and things. And a lot of that work of converting some of those, that stored chemical energy into another form, requires your body to use a lot of energy itself. So a lot of energy is lost there in that conversion process. Another way of phrasing it is, there's no way to have 100% efficiency when you're converting from one source of energy to another, or one type of energy to another. So for example, like the car here, if this car is gasoline, there's a certain amount of chemical energy that's stored in the gasoline, and only 250 kilojoules out of some millions of joules that may have been stored inside the bit of gasoline that was used to accelerate that car from 20 to 30 meters per second. Okay, so it requires much more than 250 kilojoules to accelerate that car in practice. But the amount of net work done by the force, the net force on the car, would be 250 kilojoules. So hopefully that illuminates a little bit about how that works there. So now, if there are no questions, we can go on to the next section, which is potential energy. So are there any questions? Okay, so let's go ahead and jump into the idea of potential energy. Potential energy is going to be energy due to your position. So we start by just giving a brief kind of description of potential energy like that. So we have kinetic energy, which is energy due to motion, and potential energy is energy due to your position. Energy due to position. Now, for kinetic energy, we can always define it. It's defined through the velocity, and that's the end of the story. So if something is moving, it has kinetic energy. But in a lot of cases, we cannot assign a potential energy to something. And I'll explain when we can and can't here in a moment. Energy due to position. But first, before we do that, let's take a look at a simple scenario here where, again, we just kind of have some crate or block with mass m. And we're actually going to lift this block into the air against the force of gravity. Okay, against the force of gravity. And so now the displacement, instead of delta x, I'll write the displacement as delta y. Okay. Or we could think of it as maybe delta y is equal to the height that this mass is above the ground. Okay. Now, how much work would we need to do in order to lift this mass above the surface of the Earth by an amount delta y? Well, we start with the expression that the work is equal to the parallel force times the displacement. And in this case, we'll use delta y for the displacement. There is a force of gravity acting on this object. The force of gravity is downward. The force of gravity is downward, and it is equal to mg, actually with a minus sign here, mg. And so we would have to apply a force equal and opposite to that force. If we wanted to move this mass up, we would have to at least match that force. So our applied force, we'll call it F applied there. It has to be at least as big as the force of gravity. Okay. In other words, it has to be bigger than or equal to. If we move the mass really slowly with a small velocity and a force that is equal to the force of gravity, we can write that the work done here is that we do, the work that we do is equal to the force of gravity magnitude. Actually, let's write down one more step here. So we called the force that we're applying F applied. And F applied is in the same direction as the displacement. And it's a constant force. And its magnitude is equal to the force due to gravity. So no cosine theta showing up here. The applied force is in the same direction as the displacement, so there's no minus sign. But now I'll go ahead and substitute in that our applied force has the same magnitude as the gravitational force. And then we'll drop the magnitude sign here and we'll just plug in mg times delta y. Okay. And then maybe if you want to, you can also say mgh, which I see this formula in some books writing mgh instead of mg delta y. So whatever your preference is there. And so we've calculated the amount of work that we have to do to move this block up a distance h above the surface of the earth. But we've assumed that the applied force, the force that we use to lift the object, is equal and opposite to the force of gravity. So kind of hidden in that assumption is that we're really slowly lifting this mass up, okay, with a velocity that's really close to zero. So it would really, in practice, it would take us a really long time to do that. And so this amount of work that I've written down here is only the amount of work that we would do in the case where we move the block very slowly. How would things change if we had friction involved? If we had friction involved, then there would be another force opposing us, like the force of gravity is opposing, and we'd have to apply a slightly larger force in that case. And so the amount of work here that we've written down that we have to do is really the minimum amount of work that we have to do to lift that object, a displacement delta y above the surface, okay? So this is, and that's an important point here. So this is a minimum. The minimum amount of work needed to lift the block an amount delta y above, or let's say rather than above, let's say against gravity. And so if our applied force is equal and opposite to the gravitational force on this object, what is the net force on the object? Well, we could think about a summation of forces, right? So we have the applied force plus the gravitational force, but these are vectors, and one is in the opposite direction of the other, and they both have the same magnitude. And so the net force is 0. And of course, if the net force is 0, then the net amount of work done is 0. Okay. And if the net amount of work done is 0, then the change in kinetic energy is also 0. So what that means is by lifting this mass, when we lift the mass all the way up that distance, h, or delta y above the surface of the Earth, we do so very slowly with vanishing velocity. So a velocity approximately equal to 0. So it takes us a really long time to do that. And then when we get up to the top, we just hold it there, and we just match the force of gravity there. And this object has gained no kinetic energy in the process. The final velocity is 0, the initial velocity is 0. And during the moving process, we've had a velocity which is approximately equal to 0. Okay. So with this in mind, we kind of don't gain any information about this system because we have that the network is 0 and that the change in its kinetic energy is 0, but the state of the object has changed. It's now no longer on the floor, it's all the way up in the air, a distance h. So how do we encapsulate that change in the state of the object's position? Well, we define a new kind of energy called potential energy. And in fact, this is potential energy for a specific case. So this is gravitational potential energy. Let me go ahead and say PE for potential energy as being equal to mg delta. Oh, well, let's use mgh here for a second. So the potential energy here for this situation, the gravitational potential energy is mgh. Okay. And the way we understand the potential energy is that if we were to let go of this block, let me scroll up a little bit. If we were to let go of this block, clearly the block would begin to fall back towards the surface of the Earth, right? Because the force of gravity is acting on the block. And so what happens is the block is going to begin to accelerate with an acceleration equal to g, right? 9.8 meters per second squared. And eventually it's going to return to the surface of the Earth from where it came, right? And it's going to have a velocity that it collides with the surface of the Earth with, right? So this guy's going to accelerate. It's going to build up velocity as it falls down back towards the surface. And let's go ahead and calculate what that velocity would be if we let this mass fall, okay? So we define this potential energy as mgh. If P equals mgh, does that mean only height affects potential energy? Right, so potential energy is energy due to the position of an object. So no velocity or acceleration comes into play here. So only the height or the displacement. It's really not the height, it's the displacement. So it's like a delta y, but for now, just put mgh. We'll clean that up here in a second. So we define the potential energy as mgh, but, well, what about kinetic energy? Okay, is there a connection here? So how would we calculate the velocity, the final velocity that this mass has just before it hits the surface or hits the ground? So does the question that I'm asking make sense here? This is basically like a chapter 2 type of question here, right? So we're saying we have a box that we've lifted up into the air, right? And now we're going to drop the box, let it fall, and calculate its velocity just before it collides with the ground. Okay, so that's the problem here that we're doing. So we have a mass. I'll just go ahead and redraw here. It's going to accelerate down towards the surface. And it's a distance h above the ground. It's going to end up here at the surface again. The final velocity for an object is given by its initial velocity plus its acceleration times the amount of time that it accelerates, right? Actually, I think I've been using I for initial. So let's go ahead and put I here. And what is the initial velocity? Well, if we lifted this mass up and then we just drop it, right, it's at rest. So this is 0. And the acceleration here is minus g, because this object, when we drop it, is going to be accelerating under the influence of gravity. And so the final velocity here is equal to minus gt. And so the next thing that we would need to do is to figure out how long it takes for this object to fall. I need to close some of these extra boxes here so I can use the space over here on the side. Second. Okay. So how long is it going to fall? Well, this object is a distance h above the ground. So actually, let's use y here for a second. So y final is equal to y initial plus v initial times time plus 1/2 AT squared, right? The final position of the block is going to be 0 because it's going to be at the ground. The initial y is going to be h. The initial velocity is going to be 0 again, right? Because we drop this thing from a height h. If we just drop it, we don't throw it, it's 0. And then, of course, our acceleration is going to be minus g. Those of you who remembered the formula for how long it takes an object to fall, you could have probably skipped some of these steps here, but just kind of going through it here. So if I move the h to the other side, I have minus h, but I have a minus sign on the other term as well, right? So we have h equals 1/2 gt squared, and we can solve for t from this. If I multiply the 2 over and I divide by g, I have the square root of 2h over g. And that is how long it takes for this object to fall. So now we're ready to take this time, and maybe this arrow here, now we can remove that arrow and make a new arrow here. We can take this now and plug this in for t. We have to be a little bit careful here with the algebra because we're dealing with a square root, but it's not so bad. It is minus g times the square root of 2h over g. And now whenever you have something outside of a square root, you can bring it inside the square root as long as you square it. So really we have minus the square root of 2h g squared divided by g. And we can cancel those g's there. Cancel, cancel. And finally, we have that the final velocity is minus the square root of 2h times g, or g times h. I think it's more commonly written as 2gh. So I'll go ahead and switch the order there for you guys. And of course, if we're interested in just the magnitude of the velocity, in other words, the speed that this thing has when it reaches the ground, we can drop the minus sign as well. So if we're just interested in the magnitude here, then we can just put a plus sign. Okay, and so the speed of this object is going to be equal to the square root of 2gh. Okay, we lifted an object. We did work to lift an object up a distance h above the surface. Then we let that object fall under the influence of gravity, and we calculated a speed for that object. Now that we have the speed, we can calculate its kinetic energy. So let's see what happens. So the kinetic energy is equal to 1/2 mv squared, right? Okay, we just calculated v. So let's take v here and plug it in. And we get to square it. Look at that. The square root cancels out, right? So 1/2 m times 2gh. Let's go ahead and write the square root in there and then square it. So the square and the square root cancel, leaving us finally with mgh for our answer. And so look at that. So the way that we understand this now is that if we do work on an object to lift it up into the air, we've given it some potential energy. And then if we want to, we can drop that object and all of its potential energy converts into kinetic energy. Okay, so this is like the aha moment, the eureka moment. Okay. Eureka. I don't even know if I'm spelling this right. Eureka. Does anybody know if this is spelled correctly? So potential energy. So if there's a change, well, let's not go there just yet. So the potential energy converts oh, just one E. Okay, just one E. Let's fix it up. There we go. And we can just pull this closer. And now you guys can see I never actually made a mistake in the first place. Okay, so now potential energy converts to kinetic energy. And that's nice because we've called these things energy, right? And that's the idea behind energy, is that you can have many different kinds of energies, but they're all kind of the same, and you can convert between the different kinds of energies. And that's a lot of the history of how physics developed. So for example, a lot of people would talk about, and actually we'll probably talk about this in the second semester. I think, yeah, in the second semester, you guys will talk about heat energy, for example. And then there's also things like chemical energy, nuclear energy and things. And all of those different kinds of energies, electrical energy, you can convert between those kinds of energies. So they're all the same, kind of like one and the same thing. They're all energy, but they're just in different forms. So that's the whole idea that we're kind of working towards here. Or well, we've kind of just got there. We kind of just got there. So we can convert between potential energy and kinetic energy. And the other thing is too, you can flip this problem upside down. And you can come back up here to this mass, and you could imagine, excuse me, you could imagine that you blasted this thing like out of a cannon, right? So you point your cannon vertically like this, and you shoot this mass upward with an initial velocity, which is equal to the square root of 2gh. And if you do that, well, it begins with kinetic energy of mgh. And so all of that kinetic energy will convert to potential energy as the mass travels higher and higher and higher until it reaches its highest point. And once it reaches its highest point, it will not have any kinetic energy anymore, and it will have all potential energy. And its potential energy will be equal to mgh. And so this is the idea of conservation of energy. So this is like a big one here. So actually I don't think that asterisk is enough to emphasize. So we're gonna have to break out the big guns here. So this is one of the biggest takeaways that you want to get out of a physics class, is this idea of conservation of energy. Okay, and what do we mean by conservation of energy? Well, we mean that energy cannot be created or destroyed. We can only convert between different types of energies. I'm going to go ahead and type this out because it's be difficult to write out the whole thing. So conservation of energy. Energy cannot be created or destroyed. Energy can be converted between its different types. And then let's give some examples here. So like, for example, lifting a mass against gravity gives it potential energy due to its position. That potential energy is then converted to kinetic energy if we allow that mass to fall under the influence of gravity. Okay. A little bit of a long one there, but the main point there is the first two sentences here. So maybe we can bold these and underline it. Okay, so that's the main point there. Because energy cannot be created or destroyed. It can only be converted between its different types. And so you might be wondering, actually, let me give you guys like a minute to copy that down. Okay, so just let me know in the chat when you're done copying that down, and then I'll talk a little bit more. So are we almost done copying that down? Do we need some more time? We have one person done, two people. Remember, this is going to be recorded and posted too, so you probably don't even have to write the whole thing down, but it is one of those big things that you want to take away. You know, in 20 years, you've already, taken this class and you've forgotten most of it. This is like one of those things that you want to be like, of the couple things maybe you remember in 20 years, this has got to be one of them: conservation of energy. Okay. All right, so we'll go ahead and move on. The next thing I want to talk about, the next section is very brief, and that is the idea of a conservative force versus a non-conservative force. So in order to define, and this is also more technical stuff. Let me just type some of this out. Maybe you guys can copy it again. I'll try not to make it as long as the last one though. So to define potential energy, the force that you do work against must be conservative. Must be a conservative force. Let's write it that way. So what do I mean by conservative force? Not conservative like conservative versus liberal. It's not a political thing. There's a mathematical definition of what a conservative force is, and it really stretches beyond the math that we can do in this class. And so the best way to define what a conservative force is for like a 205, 210 class would be to say what a non-conservative force is. And then the stuff that isn't non-conservative is your conservative forces. Okay. And so we cannot define a potential energy when the work is done against a non-conservative force. Okay. And then I think I don't really need to type anything more than that, so we'll leave it at that. I can write with you guys here. So, for example, well, let's just say, so we understand the meaning of a conservative force by knowing, or rather by understanding what a non-conservative force is. Now we'll draw a red arrow here. Okay. And so a classic example of a non-conservative force is friction. Okay. And maybe even we could be more precise about this because there are many different kinds of friction. So sliding friction, right? That's the kind of the friction that we've dealt with, static and kinetic sliding friction. You could also have air resistance is a type of friction, or air drag, or a drag force, kind of all the same thing, air resistance. So examples then of a conservative force would be any constant force. Any constant force is a conservative force. Any force which depends on a radial, any force which is directed in the radial direction, in other words, a central force, maybe I should write it that way, central force. So forces which only depend on R, like the gravitational force, that's a conservative force. Another example of a central force is the electrostatic force that is talked about in the second semester of this course. I say the electrostatic force because the full electromagnetic force is not necessarily conservative. It can be conservative under certain conditions, but in general, it is not conservative. Matter of fact, magnetic forces in general are not conservative. Okay. And so everything that we're going to work with, and let me give you another example actually that we already talked about. So Hooke's law is actually a conservative force. It's a variable force, but it's a conservative force. So Hooke's law, that is a conservative force. So we can, and actually we calculated the amount of work that it took to stretch the spring, right? You guys remember that? So that amount of work that we did to stretch a spring, so Hooke's law, look at this, full circle here, right? Hooke's law, we calculated the net work and it was minus 1/2 K times delta X squared, okay? But the restoring force is the force that we're doing the work against, which is opposite to our applied force. And so when we calculate the net work, we got this negative 1/2 K times delta X squared. But the potential energy is 1/2. So the change in potential energy is 1/2 positive K times delta X squared. And so actually, this is a nice example. I'm glad I brought this back up because now this allows us to write down the connection between the net work done on an object and its change in potential energy. And as you guys can see, these two quantities differ by a minus sign, right? So here's the minus sign right here. Okay, they differ by a minus sign. So the net amount of work done against a conservative force is equal to the negative of its change in potential energy. And by the work energy theorem, the negative of the change in potential energy must then be equal to the change in the kinetic energy, because the net work done on any object is always equal to its change in kinetic energy. And so now we have a new formula here. And this formula is basically what we already understand. It's that potential and kinetic energy can be converted between one another. So if we wanted to have a formula that tells us we can convert between these two energies, this would be that formula. So we can convert between potential energy and kinetic energy. And this equation is a very nice equation for understanding how energy works. You have to have a change in the potential energy in order to have a change in the motion of an object. In other words, a change in its kinetic energy. Remember that kinetic energy is proportional to the velocity squared or the speed squared. It's the same thing in this case. Because it's being squared, it doesn't matter if you use velocity or if you use speed. So it tells us that the potential energy, in a certain sense, the actual value of it doesn't matter. Only the change in potential energy matters. So what does that mean? Well, what it means is if I have a table here, which rests on the floor, and then somewhere over here, there's a hole in the floor. Okay. I could imagine having a book that rests on this table here. Okay. And I could lift it up a distance h above the tabletop. And so now it's like up here. And there's some potential energy associated with that. There's some value of the potential that I could assign. If I say this here is y equals 0, and this up here is y equals h. But someone else could come along and they could define their coordinate system differently. They could say, no, I don't like y equals 0 for the table because the table's above the ground. I like to define 0 at the ground level. So I say y equals 0 is here at the ground. And then that person would say, okay, this is the height of the table, which let's say the height of the table is h sub t. Let's go ahead and get a dotted line here. Plus the height that the object is lifted above the table, right? But if that book is dropped up from a distance h above the table, it will eventually smack into the table and it will only lose potential energy equal to mgh. So as that book falls down, it will only lose potential energy minus the change in potential energy would be equal to mgh. If it falls, if it's falling, it loses potential energy. So it starts at mgh and it's at a lower potential, excuse me, I misspoke there. The potential energy of the book at its highest point would be mgh for this. So let's be precise here. So this is the, let's call this state 2 and let's call this state 1. The potential energy according to this person with their coordinates at the location 2 at state 2 would be mgh. And the potential energy at state 1 would be equal to 0. Okay. Now person number 2 over here, and maybe I should have drawn this in different colors here. Let's maybe make this purple. So this person, that h is the same, but they say their 0 is down here at the ground level. So y equals 0 for them here. Okay. So what is the potential energy? I'm gonna go ahead and delete that. What is the potential energy of this book in state 2 according to this person over here? Well, according to this person, the potential energy is mg, and then it's h plus ht. And what's the potential energy in the state 1 when the book comes back down to the table? Well, then the potential energy is simply mght, not 0 now. But if I calculate the change in potential energy, then what I get is, if I do final minus initial, that's potential energy. If we're saying the book is up in the air and then we drop it, that would be PE1 minus PE2. So PE1 is mght minus mgh plus ht. We're going to have negative mgh. And so this is what I mean when I say the negative, or rather, this is the change in potential energy here, not the negative. So the change in potential energy, so this is the initial state, and this is the final state, just to be clear here. When we drop this book, the change in its potential energy is always going to be related to that mgh. So it doesn't matter if somebody else comes along and decides they want to use different coordinates than you use. The only thing that matters is the change in potential energy. Okay. Then here's a hole here, right? What do you guys think is going to happen if, the red person comes along and says, no, y equals 0 is here. And, this is, the height to get up to the ground. And then, this is again the height of the table. And then again, this is the height above the table. Well, what's going to happen is, again, we're going to have this situation where the potential energy in the state 1 is mg times hg plus ht. And then the potential energy for the state 2 is going to be mgh plus ht plus hg. And then when you subtract the two, what are you going to be left with? Well, you're going to be left with the exact same thing. Again, the change in potential energy is going to be equal to minus mgh. And so in all cases, we have that minus the potential, minus the change in potential energy is equal to mgh when we drop that book. Okay, so it's only changes that are physical. So only changes in potential energy matter. Let's just do P E. Okay, the actual value of the potential energy does not matter. Only how the potential energy changes matters. Okay, so any questions about that? Did that make sense? Okay, so now I think is a good time to let's go ahead and do another example so we don't end up covering too much without doing a little something. I may need to reopen the textbook here to pull up an example, or maybe I can just come up with some numbers myself here. So here's an interesting question that often is asked. So suppose we have a ball here, has a mass m, and it falls. Let's say the ball is 100 meters in the air. Okay. It's going to have a final velocity when it hits the ground. Okay. But its initial velocity is, we're going to take to be 0. Just for simplicity, you don't have to have the initial velocity of the ball being 0. If you have the initial velocity of the ball being some value, then that means the ball starts with kinetic energy. And so as the ball loses kinetic energy, it just gains more, as the ball loses potential energy from falling, it just gains more and more kinetic energy. But it will have some initial amount of kinetic energy. So this ball falls 100 meters. Let's take its mass to be, let's have maybe a reasonable mass here, 0.5 kilograms, maybe like a basketball or something. And we want to know, first off, what is its potential energy? So what is the potential energy here? So part A. If we take the floor or the ground to be y equals 0. Okay, so what is its potential energy? Part B, what is its final velocity when it reaches the ground? Part C, what is its kinetic energy? Calculated as 1/2 mv squared. And then D, does minus delta potential energy equal delta kinetic energy? Okay, does that relationship hold? Okay. And then we'll do kind of a special calculation here. Answer E. Repeat A, B, and C for the ball. When it reaches 50 meters. Okay. So you'll calculate the potential energy again. You'll calculate its velocity when it's only fallen 50 meters. And you'll calculate its kinetic energy as 1/2 mv squared. And then again, you'll check if minus delta PE equals delta KE. And then finally, this is a big example, huh? Finally, F, what is the total energy E equals potential energy plus kinetic energy. And then we could add to that further, we could say FG does E agree with A and C? Okay, long example there. Let me try to compactify some of this stuff here by moving it a little bit closer. Move it up a little bit, save some space, save some space. Okay. Just trying to get this all on one page here real quick. Whoops. Oh no, I went too far there. Get all this one page. There we go. Got up a little bit of editing here. There we go. That should fit there. Okay. Okay, so this example here will be the last example that we do. So if you can't finish this example by the time 8:50 comes around, class ends at 8:50, right? Go ahead and finish the problem anyways, kind of on your own time, because it's very helpful. Excuse me. It's very helpful to go through at least one problem like this, where you kind of calculate everything at like different stages of the motion and prove to yourself that all of the physics is self-consistent, like everything is working everywhere in the problem, as we've kind of shown that it should. We want to check for ourselves that it's working at every stage. So that's the idea behind a problem like this. So it's a lot of parts there, a lot of moving parts, but go ahead and work on this, and let me know in the chat if you have a question. If you feel confident that you don't need my help to do this question and you can do this on your own, since we're really close to 8:50, the end of class, feel free to just leave the meeting. I won't lecture any more than what we've already gone over. There is maybe one other interesting topic at the end of the chapter, and that is energy with dissipative forces. In other words, how do we account for all of the energy if we have friction in our problem? And essentially what you do is you calculate the work done by a friction force, and you just subtract that from the overall energy. So if you have kinetic energy and that kinetic energy is being converted to potential energy, but you're working against some friction force like air resistance, then you would calculate how much work that air resistance force does on your mass or your object. And then you would subtract that from your overall answer at the end. So it's a fairly simple modification. Just subtract out the work done by the friction. You can put answers in the chat kind of as you get them. Does anybody have the potential energy of this mass at its highest point here? Good, right. Exactly, 490 joules. Does anybody have the final velocity yet? To get the final velocity, you kind of have to work with that stuff we kind of developed earlier, the √2gh. So 44.3 meters per second. Let me go ahead and get my calculator out and I can go ahead and confirm that for you guys. Yep, so 44.3 meters per second is good. Does anybody have the kinetic energy calculated as 1/2 mv squared? So if you calculate it using 1/2 mv squared, then you should get an answer that is slightly different than the 490 joules that you got before. Kevin, your answer seems quite a bit off. Double check your calculation on that. So yes, so it should be maybe a little bit different than the 490 joules because you rounded your velocity. But if you use your exact velocity, you will get exactly 490 joules, right? So we calculate this one, we get, maybe let me change the colors here. So we calculate it as mv squared, and we get approximately 490.6 joules. But of course, we know it should be exactly 490 because of part D, right? So does the negative change in potential energy equal the change in kinetic energy? Well, this thing starts with 490 joules, and then its potential energy at the ground is 0. So what's the change? So we do potential energy final minus potential energy initial. So what's the change in potential energy? 490, right? And then we take the, is negative 490, and then we take the negative of that negative answer to get 490. And we know that this thing wasn't moving, and now it is moving at the bottom, and it has 490 joules of kinetic energy at the bottom. And so, yes, this is 490 joules. And so minus change in potential energy equals the change in kinetic. Question E, repeat A, B, and C for the ball when it reaches 50 meters. So what happens in this case? So its potential energy at 50 meters is going to be how much? By the way, it is 8:50 p.m. So if you're comfortable with this question, feel free to leave the meeting. I won't cover any new material. Right, exactly, 245 joules, right? It's going to be exactly half because it's half as high above the ground. So good. So we'll go ahead and write that in over the go ahead and write that in over part A there, 245 joules. For part B, what are we going to get? The velocity when it's 50 meters above the ground. That's maybe a little bit more tricky to get that. You can again use square root of 2gh, but this time you have to plug in h is the distance that the object fell, right? Well, if it's 50 meters above the ground and it started at 100 meters, then it only fell 50 meters, right? And so you could do square root of 2g times, square root of 2 times 9.8 times 50. You get roughly 31.3 meters per second. Notice that's not half of the velocity, right? That's not half of the velocity. That is 1 over square root 2 of the velocity. So divide the velocity by roughly 1.4. And remember, it has to be that way because remember, the displacement goes like t squared. The velocity goes like t times the acceleration. And for part C, what is the kinetic energy calculated as 1/2 mv squared? Somebody have it? 245 joules, but what is the answer if we use exactly this 31.3 meters per second? It's going to be slightly different than the 245. Yeah, so let's put that 244.9 joules. So we know it should be exact if we use the exact velocity, but the idea is to use this number here to really see. Okay, so good. And then what is the total energy, part F? What is the total energy when the ball is at 50 meters? Well, What's the potential energy? 245 joules. What's the kinetic energy? 244.9 joules. If we add those up, we get 489.9, which is the 490 joules that we started with, right? The 490 joules that we started with in the beginning, that is our total energy. And so since we can only convert between different types of energies, the total energy should always be the same. So if we have only potential energy, then if we let that object fall down some distance, it doesn't matter how far it falls. If it falls down some distance y, then its kinetic energy plus its potential energy have to add up to the same number, whatever the potential energy was at the start. So the last part, does E agree with A and C? What's the answer? Does the total energy agree with what we calculated at the top when it only had potential energy? And does it agree with what we calculated when it was at the bottom when it only has kinetic energy? The answer is yes, exactly. So that's energy in a nutshell for you guys. So hopefully you're well equipped to tackle the homework problems. Again, the last thing I already mentioned, there's a section on energy with dissipative forces. All you have to do is calculate the work done by that non-conservative force, which is typically a friction force, and subtract that from your overall energy. And then you apply the same analysis here with the negative of the change of potential energy is equal to the change in kinetic energy. And you can always write down the total energy is just your potential plus your kinetic. Can you explain again why minus delta PE equals delta KE? Yes, it has to do with the fact that the law of conservation of energy tells us we can't create or destroy any energy. And we started by developing this idea of work, and this net work that we do on an object adds to that object's kinetic energy. Okay. And then we said, well, wait a minute, what if we do some work on an object with our applied force, but our applied force works against, let's say, gravity. So we apply a force, but that force on that object works against a gravitational force so that there's no net force on the object. The net work done is 0, but the work done by the force that we applied was mgh. And so the work done by the force of gravity must be minus mgh, right? And then we called this potential energy. So we called that potential energy. But notice that the change in potential energy there is negative. Okay. And so the work done by a conservative force, just to really sell it here, it has to be done by a conservative force, which the force of gravity is a conservative force, is equal to minus the change in potential energy. Of course, the net work is always the change in kinetic energy. So if we reverse the logic now, instead of lifting an object up against gravity, we just start with an object that's already lifted and we just let it go. Well, then it has some potential energy already. It has mgh. And if it falls, it loses potential energy. right? So it's 0 down here. It's mgh up here. Let's write it this way. So it's mgh up here. It's 0 down there. As it falls, its change is negative because the final is 0 and the initial is mgh. So the change is negative mgh. So we need to have that minus sign when we define the potential energy. We have to say that the work, the net work here, and the work is done by the gravitational force now. The work is being done on that object by the gravitational force. Okay. And the gravitational force is a conservative force. And so the takeaway from that is that whenever we have a change in kinetic energy, that will be equal to the negative of the change in potential energy. Okay. All right, so feel free to leave the call. If there are no questions, I'm going to go ahead and end the meeting. We're already 10 minutes over. Thank you guys for coming and listening. Good luck on your guys' homework assignments. Okay, so I'm going to go ahead and end the recording.